Hello and welcome back to another episode of Math with Sohn. Today we're going to be doing a linearization problem, and this one is a little bit more difficult than some of the other ones we've done. We have a scenario where we have a coin, it looks like, swirling around on a table, and that swirling around is being caused by the fact that it is being pulled inwards by this bigger mass, probably bigger mass, m2 times g. The force going down here is causing a force centripetal. Now, if you're at the very beginning of your physics lessons and career, this bit is going to be confusing and hard, but luckily they have divided it into where deriving the expression, they tell you what to derive, okay? And then they ask you to linearize it, okay? So the first thing we're going to do, or would be expected to do, is derive this expression. If you're only here for the linearization aspect, if you're only here to learn how to linearize, then I recommend skipping like 5-ish minutes further into the video until we start doing this graph. So to start the linearization thing, if you're worried about that, you need to find an experimental value for g. So g would need to be the slope. We're going to get that in 5 minutes. We're going to do the physics now. So here, we have to first understand that force centripetal actually is equal to mv squared over r. Acceleration takes away the m. Okay, so force centripetal is mv squared over r, which is probably on your formula sheet. Almost everything is on your formula sheet in physics. And that force centripetal is being caused by the mg going down. Okay, so that means that m2g is equal to m1. It is this mass, v squared over r. If you don't get that right this moment, not the end of the world. If it's the beginning of the year, if it's the end of the year, I hope you understand that this pulling down is causing this inward force centripetal. Okay? So with that in mind, that would be great if this was all you had to do, but they have period here. And the period is the time it takes to go around one time. If the period is the time it takes to go around one time, the distance is 2 pi r. All the way around, a circle distance around is 2 pi r. If you divide distance by rate, which would be the velocity, then you get the time, because delta x is equal to vi times t type of deal. If you divide delta x by time, you get velocity. If you divide by velocity, you get time. Okay? So we had the time, the period is the time. So we are going to need to connect this and this in some way, which is not the easiest thing to do in this particular case. Part of AP physics is just trying, even when you think it shouldn't be that hard, it sometimes is. Sometimes it's super easy, sometimes it's not. We need to solve for p. We need to look through this equation. We're allowed m1, we're allowed m2, we're allowed r, we're allowed g. What we're not allowed, apparently, is velocity. And notice how both of these equations have a velocity. So you need to solve for velocity. And I am going to solve for velocity in this equation because it looks a little bit easier. It might be bad, like it might be a mistake to solve for velocity there. But I'm going to do that now. So if I do that, p times v is equal to 2 pi r. If I divide by p, we get velocity as 2 pi r divided by p, because that is an inverse relationship, so those can just swap. So this is what velocity is equal to, and then I can plug that in for the velocity over here, and that would eliminate everything. It would allow me to have all the variables what I was allowed, which was the m, the radius, and everything except for velocity, and would also incorporate the fact that we have the p, the period, inputted in. So we got m2g is equal to m1. We're replacing v with all of this stuff, which is 2 pi r over the period quantity squared divided by r. And then we just do a little bit of math. We get m2g is equal to m1 times 4 pi quantity, so it would be 4 pi squared, radius squared, over p, divided by r, would equal, that's what it equals. So now we have to continue simplifying. We're going to eventually need to solve for p or get p by itself. So I am going to multiply by r because I don't like this r here. m2gr is equal to m1 4 pi squared r squared over period. Now from here, I am going to multiply by p to get that off the bottom. P m2gr equals m1 4 pi squared r squared. I don't know why I put the parentheses because they don't need to be there anymore. Now I'm going to solve for p, so I'm going to divide by m2, I'm going to divide by g, I'm going to divide by r, and go from there. And I'm also going to realize I made a mistake. See how this squared is here? This should be a p squared once we distribute it. So this is a p squared. Whew, that could have been bad. Let's solve for p. So p squared, we get m1 4 pi squared r squared divide by m2 gr. One of these r's will cancel. And then we have to square root everything. So we get p is equal to the square root of m1 4 pi squared over m2g. And if at that point you didn't think you were doing it right, you're about to find out that you were. The square root of 4 is 2. The square root of pi squared is pi. Square root of m1, don't forget the r over m2g. Is this what they expected us to find here? We got 2 pi, m1r, m2g, square root, everything looks good. We would get the points for that. Okay, now even if you couldn't derive the equation, sometimes if it's a hard equation, they give it to you. And now we get to the linearization part, which is about 5 minutes into the future. If you joined me now, we're filling in the chart. We want to find the experimental value for g. Everything that is constant, now let's think, there's a lot of things that are held constant. The mass 1 was probably held constant. The mass 2 might have been held constant. The radius might have been constant. So let's see what changed. Well, we got mass 2 was changed, okay? And due to that, the period changed. So that means that when we look at this, this is going to be the y value, the y, and we changed m2. That makes m2, in a way, not m2 by itself, the x value. And if we want to find the experimental value for g, I'm going to put 2 pi. I'm going to rewrite it. I need to peel off that m2. So this is going to be the square root of m1r over g times the square root of 1 over m2. So all I did was separate off that m2, and because they're all multiplied, I just wrote times square root of 1 over m2. That makes all of this stuff right here the slope. All of it. Every bit. And that makes this part right here the x value. Now, it didn't have to be that way. We could have put, the m1 and the r and all that part with the m2. I prefer to have my slope be big and my x value be small because I have to do a lot of x values and only one slope. So I'm going to make the slope the square root of, not the slope, the x value, the square root of 1 over m2. So we have to calculate all those values, and then we will be able to graph it on the line. Okay, so I'm going to do that real quick. We got the square root of 1 over m2. So we got the square root of 1 divided by, I got to do all the values, 1 divided by, that did not help, 0.02, which is 7.07. Then we got to do 1 divided by 0.04, which is 5. Bad looking 5. Then we got to do 1 divided by 0.06, which is 4.08. And then we got to do 1 divided by 0.08, and we get 3.53 and 3.54. Okay, so that is all of our values for 1 over the square root of m2. And then it says what quantity should be graphed to yield a straight line. We already did that. We would need to graph p against, p is the y value, against the square root of 1 over m2 as the x value. Okay, so let's do that now. We got 1 over the square root of m2, and you could put that all under the over the square root, or just as I have done it, and that is going to be in kilograms, and technically it is just kilograms. Even though you're square rooting it, the unit is still a kilogram, okay? Which is weird. I don't think it's 1 over kilograms. Is it 1 over kilogram? I gotta think. I don't know. I'm gonna go with kilograms. It's still a kilogram, even though we're dividing. All right, and then we have P, which is in seconds. Okay? It's 1 over square root of kilogram. 1 over kilogram? Yeah, it's 1 divided, 1 over kilogram. We might do a unit analysis at the end, but this video is already getting long. So now let's plot the values. We got 7.07 to 3.53. We should probably start at 0 because this had no y-intercept. So we have 0 here, and I have to go from 0 to 7. So if we counted by 1, 2, 3, 4, 5, that's not going to do it. If we count by 2s, 2, 4, 6, 8, we should be covering more than half of the graph with that, so I think we're okay. Maybe not with 3.54. Maybe I should pick a different number. Maybe we count by 1.5s. 1.5, 3, 4.5. I got to do math. What is 5 times 1.5 is 7.5. That'd be better. So let's do 1.5. That'd be 3. This would be 4.5, 6, and then this would be 7.5. That is a little bit better of a scale because we're starting at 3.54, and you have to use more than half of the graph. Here, we have a 0, essentially, all the way to 1.4, so what should we scale that one by? Take your time to scale things. So we should maybe count by 0.5s, 0.5, 1, 1.5. That's not good enough. 0.4, that seems okay. 0.4, 0.8, 1.2, 1.6. Maybe could have picked a better one than 0.4. 0.35 seems weird. I'm going to keep 0.4. It might not be large enough vertically, so you might have got dinged if you pick that. So take your time with it. Now I'm second guessing myself. I'm going to do 0.3. 0.3, 0.6, 0.9, 1.2, and then this would be 1.5 at the top. That's better. That's much better. Okay, so plotting our first point, we got 3.54. 3.54 is... Here we're counting by 1, 2, 3, 4, 5, and that is 15. So each of these are 0.3. Okay, so 3.54, and then up to 0.75 would be right about there for that first point. I need to zoom out a little bit. There we go. Okay. The next point is 4.08 and 0.8. 4.08 would be 3.3, 3.6, 3.9, 4.08 is around here, and then it would be up to 0.8. So 0.8 is roughly there, looking like a line so far. And then we got 1.05 and 5. 1.05, it's kind of weird that they're jumping all around, but that's okay. 1.05 is, here's 0.75, 1.05, that's 0.3, 0.6, 0.9, so 1.05, and then that's the x value, that is it's 5, and then it is 1.05. I went the wrong way. 5 is here. 5 and 1.05 would be roughly there. Got it. Messed up the x and the y. And then lastly, x is 7.07, so that would be about here, 7.07, and it would be going up to 1.4. 7.07 up to 1.4. Okay, if we look at this, what do you notice that seems a little off? Do we use the majority of the y values? Seemingly not. Okay, do we use the majority of the x values? Yes, that seems maybe more than half of the graph. So that is something that you need to be very careful of, because we would get dinged for not using correct proportions there. If you've already graphed everything and you want to just accept your losses like I do, that's where I'm at right now. So I'm going to accept that we would not be getting full credit, and we should have scaled it differently. I already scribbled it out once. So let's find the actual slope of this graph. You cannot pick points that are on your graph. You have to pick points that are not on your graph. I am going to pick the point here, which is, let's pick points far away. Let's pick this point right there, which is 7.5, comma, it is up by 1, 2, 3, so that would be 1.1, 1.2, 1.3, 1.4, 1.5, 1, 2, 3, 4, 5. And that is seemingly difficult to find. What is the difference between those two? We picked a very funky scale. 1.5 minus 1.2, divide by 5. It is 0.06 each time. So this would be 1.26, 1.32, 1.38. And then this is 1.54. No, 46. 4. Got it. Okay, so this point right here is 1.38. Annoying. And then I'm going to pick an easier point. That point right there is 1.5, comma, 0.3. 1.5, comma, 0.3. Use your slope formula. We would have to do 1.38 minus 0.3 over 7.5 minus 1.5. You get an answer to that. 1.38 minus 0.3 divided by 7.5 minus 1.5 into my calculator tells me my slope is 0.18. But wait, there's more. That's just the slope. The slope earns 1 point, finding the experimental value for gravity. Make sure your line of best fit does go above, below, above, below. They only had 4 points. That's not a lot. So that is your slope. What did our slope originally equal? Well, our slope originally equaled 2 pi square root of m r over g. So we have to do 0.18 is equal to all of that stuff. 2 pi, pi is a number, square root of m r over g. Now, pi I can plug in, so we get 0.18 is equal to 3.14. Don't forget your 2. Square root of mass 1. Mass 1 is provided somewhere. It is 0.012 up here. And r is provided 0.08. So it is provided for mass 0.012, provided for r, which is 0.8 according to the problem, divide by gravity. We don't know what gravity is. We know it's 9.81, but we're going to see if we get that when we solve for gravity here. Okay, so let's do the math. We get 0.18 g is equal to, oh no, I can't just do that. Let's just type in all the numbers. 3.14 times 2 is 6.28 is equal to the square root of 0.012 times 0.8. 0.0096 over g, still all in the square rooty, is equal to 0.18. I'm going to divide by 6.28. 0.18 divide by 6.28, and I get 0.0286 is equal to the square root of 0.0096 over g. I'm going to square both sides to get rid of the square root. And then I'm going to multiply by g. So I squared both sides. I got an e number, so that's annoying. And then I got to multiply by g. So this is going to be g times my answer is equal to 0.0096. So I have to do 0.0096 0.0096 divide by the answer to get an experimental value of gravity of 11.68, which is not great, but it is close to 9.81. We would have done better if we had picked a better scale. So it goes back to the idea that you want to really utilize as much of the graph as possible so that when you find your slope, it's more accurate. Okay? That's going to do it for this one. Sorry it took forever, but sometimes these take a while. This is supposed to be it's a 15-point question according to the top, which means it should take 25 minutes, and it took me 19 to explain it. Okay? That's going to do it for this one. See you later. Bye.